Hello everyone and welcome to another solutions video. Yes, I am back and today we are going to be discussing solutions for 764 Division 3. Don't ask me why I didn't make for Goodbye 21 and Hello 2022. Reason was one went very bad and for one I slept through it, so that's why I didn't make. But that aside, let's continue with the solutions. So problem A. In this problem, we have an array. Okay, so a1 a2 up to an, and we can do an operation. So let's define what the operation is like. Let me just make a partition here. So what the operation is, we choose some indices. Okay, so let's say i1 i2, we can choose any number of indices. So let's say we choose k indices, and then what we can do is, for all j from 1 to k, we do plus plus. So basically we choose some indices and then we increment all the indices, all the elements at those indices. So let's say if the array was 1 2 3 7 and we chose index 2 and 4, then this array would become, after one operation, 1 3, as you can see, plus 1 3, and then plus 1 again 8. So this is the operation, and what we want to do is we want to make all the elements equal. So how can we do that? So as you know, we can only do increment, so that means we will have to increase the elements that are small, since we cannot change the bigger elements. I mean, we can change them, but it won't do any good to us. So here, as you can see, we want to move. So if this is the sorted visualization of our array, then as you can see, we want to move this up to this maximum point. We want to move this up to this maximum point, this up to here, this up to here, and this up to here. This will be optimal, because if we were to let's say decide that we want to reach here, okay, then as you can see, we are just doing extra operations everywhere. So that's not optimal, and we cannot do it here either, because we cannot decrease, right? This is not possible, we cannot decrease. So that is why this is the optimal place. And now let's see how many operations that takes. So let's say this is plus 1, let's say this is plus 3, plus 4, plus 5, plus 5. So in the first operation, what we can do is increment only these two. So these two becomes plus 4, right? And then in the second operation, we increment only these two again. And now, so we increment now these three, first three, because this is also 4. So we increment these three, and now they all become plus 3. So now I can increment all of these 2 times, and then everyone will be requiring plus 1, and then we can increment everything together, and we will get up to this position. And how many operations did it take? That's right, exactly the maximum difference. So yeah, there are other different ways to construct that solution, but we only care what is the maximum number of operations required. So that would be the max A. So A max minus A min. So that is the answer. Let's have a look at the implementation, even though it's very trivial. So we take input, and then I sort it, and then the biggest minus smallest. All right. So let's move on to the next problem. Make AP. In this problem, we are given 3 numbers, A, B, and C. And we can choose one of the numbers. Let's say we choose B, and we can multiply it with any value k. So multiply equals to k. We can also do something like A multiplied by equals to some k2, k1, or C multiplied by equals to k3. But we are allowed to do only one of these operations, and this number we can choose. Okay. And what we want to happen is that after this operation, A, B, and C are in an AP. That means B minus A is some D, It can be negative, make sure. And c minus b is also equals to d. So we want to check if we can do that operation once such that this becomes an AP and the ordering has to be same. So that means A is the first term, B is the second term, C is the third term. So how can we do that? Well, since we can only move or change one number, right? Since we can only change one of these numbers, that means the difference between other two numbers remains same. So if I were to choose, let's say, C, then that means let's say initially the distance was d1 and d2. If I were to choose C, which I will multiply by something, now remember, I don't necessarily have to multiply, which is equals to multiplying by 1. Okay, so if I want to multiply it by something, let's say x, right? So since only C is changing, that means A and B are fixed. So D1 is also fixed, and hence the difference required is D1. So I want D2 to be equals to D1. So I can get the target C. So the target C would be B plus D1, right? And then I just have to check that C multiplied by some natural number, right? So some natural number, can this be equals to target C? If so, then that means we can change C such that ABC becomes an AP. Now we can do the same. Let me just remove everything. Now we can do the same and try to use A. So we will multiply this by some x, right? So A multiplied by equals to x. But now since A is being choose, B and C are fixed. And this is D1 and D2. Since B and C are fixed, that means the difference has to be D2. So B is fixed, C is fixed, D2 is fixed, right? So A, the target A, is also fixed. This is also has to be D2. So target A again is our B minus D2, right? So I just have to check if A multiplied by some natural number x is equals to target A. So same as before. And then there is one last case. And the last case is that, let's call this capital D. So in the last case, I'm choosing B. So since this is being multiplied by x, right, that means A and C are fixed. So if A and C are fixed, that means this total distance is fixed. So now there will be two conditions. First of all, it has to be divisible by 2, right? Otherwise D1 and D2 can't be equal. And if it is divisible by 2, then the target B, T underscore B, is A plus D by 2, or which is also again equals to C minus D by 2. And then I just have to check B multiplied by some natural number x, is that equals to target B. I think I did it in a way too elaborate way, a little bit unnecessary, but okay. So let's see the implementation. I'm taking in the input, and as you can see, this is the first case. I'm fixing A2. Sorry, I'm choosing A2 to be changed. So as you can see, I'm checking if it is divisible and if it is greater than 0. It is exactly the same thing I have written, I had explained here, so I don't think really have to go through the code, but let's quickly go. So yeah, this difference, yeah, I'm not going through it. It's the same thing. I'm not repeating that. Okay, so now problem C. So that problem was just case analysis, so really trivial. You just have to be sure that you're not missing a case. So now the third problem, division by 2 and permutation. So what is this problem? In this problem, we have again an array. We always have an array. And what we want to do is, we want to convert it into a permutation of 1 to n. So 1, 2, 3. up to n in any order. So for reordering, I'm just going to say like this. So a permutation of 1 to n. Now what operations we can do is simple. Choose any element ai and then we can divide it by 2. And this is floor division. So if it is 4, it becomes 2. If it is 5, it again becomes 2. For 6, 3, 7, 3. So this is the division we are dealing with. Now let's see what we can do. So we just want to tell if we can convert this array into a permutation using those operations. Doesn't matter how many operations, okay? So let's see how we can do it. Let's say I had these value 1, 2, 3 and 6 and something. There are other values as well, but let's say n was equals to 5, so I want to convert into range 1 to 5. Now as you can see, this we have 3 and we have 6. Now 6 can be converted into 3, right? 6 can be converted into 3, but we're not sure. Okay, let's say we don't have this. Let's say we don't have 2, or let's say we don't have 1. Yeah, that would be good. Let's say this was the array. There were some other things like 4 and 9. So we have 3 and we have 6. Now 3 can also become 3 and 6 can also become 3 by dividing by 2, right? So how to decide which one to take, right? So in the final array, let's make the final array here 1, 2, 3, 4, 5, which we want, any permutation of that. So this 3, right? This 3 can become 3 and 6 can become 3. Now which one to take? Now I'll say it doesn't matter. Why it doesn't matter? Because see, this 3 can be further divided to become 1. But since this 6 was able to divide and become 3, it will be able to divide again and become 1. So it doesn't matter if I choose the smaller one or bigger one. If anything, choosing the smaller one will always be good enough, right? Because something that the smaller one can become, if a bigger one can become that, then it will be able to become all the values this can become, right? So 3 and then 1, but also all the other values it was able to become before that. So let's say it was 12, so it was able to become 6 and then 3. So really we just have to try to assign these values. So all these values we want to try to assign these values among one of them, one of the permutation values, and we will try to prioritize the smaller ones. So let's have a look at the implementation to get a little more idea how I'm doing it. So here, first of all, I am taking the input and then I'm storing another vector. Now this is just for ease of implementation. So what I'm gonna do is I'm gonna repetitively do the operation, right? So divide by equals to 2 for anything I want, and I'm gonna keep doing that until, okay, wait, what have I done here? Okay, so since I have to boil down every value in the range of 1 to n, right? So in this range, and I don't know how much I want to divide something. So what I did, so there are multiple ways to do it, but what I did is I will go through it and see if I can reduce anything, and if I even need to reduce it, and I'll reduce it, and I'll keep doing that as long as I can. And once I cannot do that, that means I'm done doing the operations, and then I'll just say that is it a permutation or not. Sorry if it wasn't clear. Let me explain again. So I'm doing this part you're seeing, right? So what this is just assuming that we can do operation on every element only once. So what I'm doing this operation only once here, and I'll keep trying to do this again and again until I'm not doing this operation anymore. So this was a little bit unrelated, this explanation, because this is how I did it. The key to solving it is just this, that a number that is bigger will always be able to accommodate for the smaller numbers that come in its path of division by 2, right? So I just want to assign values which assign values in a ascending order. So ideally, so there are multiple ways to implement it. I implemented it very weirdly, but so let's say I had this 4 6 13 2 and 1 2 and let's say 5, right? And I want to convert it into 1 2 3 4 5, this, right? So as you can see, I have 5. Maybe some other value can become 5, but that doesn't matter. I'll just put 5 here. Similarly, I'll put 2 here and 4 here. Now 6 can be divided by 2 to get 3, and then 13 can be divided successively by 2 to become 1. So 13 divided by 2 6, divided by 2 3, divided by 2 1. So this is the algorithm. Okay, now my implementation, which is very weird, there what I'm doing is, as you can see, for 13 I had to do the division multiple times. So to avoid that, what I did, I would say that okay, I'm gonna be doing the operations only once, and so I do that operation, and if I have made any change in the array, then I will break out of the loop, then I will continue the loop. If I've stopped doing the operations, then I will break out of the loop, and then I'll check that is it a permutation. So if permutation is a C++ function, I'm checking is A a permutation of required array, and required array is just 1 to n. So when we do iota, what it does is, so our array had n elements, right? Initially all were 0 because that's how I have initialized it, and when I do this iota 1 and starting point 1, then what it does is it makes the first element 1, the second 2, third 3, and so on. So this way I just made a dummy permutation, and I checked is A a permutation of B, and if so, then yes, otherwise no. And this part, so what I'm doing here is I'm keeping track of things that I have already filled up. Okay, so now I iterate. And check, first of all, if element is greater than n, then I obviously have to divide it, right? And in just that case, I'm dividing it too many times. But once it is inside the range 1 to n, wait, okay, if my implementation has confused me, I think we can just forget this part and just do this much. So this is the core, forget what I said. So I'm keeping a track of all the things I've done, right? And then what I'm doing, I'm iterating through the array. Now while the element is greater than n, obviously I have to divide it by 2, and while it has been done, okay, while it has been done. So for example, I have, like, let's say 6 was done, 3 wasn't done, and I had 12, so I divided by 2 to get 6. Then I see that it was already done, so I divided it again by 2. So basically I'm trying to find a spot where it fits in. So once I find a spot where it fits, if it is 0, then that means it didn't find any spot. Basically what happened, it went from whatever value it was, k by 2, k by 4, then it went to 1, and then it went to 0. So in that case, I cannot do the transformation to a permutation. Otherwise, I just insert it into the done set. So yeah, sorry about this. I don't know why I did it. See, only 2 people knew why I did this when I was doing the contest. Now only 1 person knows. That's right, no one. So that was a bad joke. So yeah, this was the actual core part. Even I got confused, what the heck have I done here? But yeah. Okay, so now problem D. That took a lot of time. Oh, the problem D. So in this problem, so this is like, this is a prime example of how to overcomplicate a simple thing. So what it says, okay, so the statement is very funny. So we have a string. Let's take a actual string like A, B, C, D, C, F, X, T, Y. So we have a string, and we are also given a number k, which is less than or equals to the length, which is n. So we have to color this string with at least k distinct colors. Sorry, with exactly k distinct colors. We don't necessarily have to color everything. So for example, if k was 2, then I'll have to color it into two things, and the others I can remain uncolored. So basically, let's say I color A in blue and C in blue, and I color F and X in green, then I can leave the other ones. But this is what I have to do. I want to color some characters, and I want to do it for k colors, and for every color there has to be at least 2 characters colored. Okay, and we don't have to color everything. Now what this boils down, right? What this boils down to, okay, no, the statement continues. So the statement after that says that now for every color, for example, the second color that was green, we had fx, right? Now we can reorder this sequence of characters in any way we want to make a palindrome. Similarly for blue color, we want to take the characters we took, but reorder them in any way, and then, or basically permute them in any way to make a palindrome. And we want to say that is it possible to do it. So I want all of them to be permutation, and then what I want is the number of characters colored by the string, sorry, the number of colored characters, the minimum colored characters, right? That value I want to maximize. So if you understood what I said, I don't know how, because it was a very confusing statement. What it boils down, right? If you think about it, what it actually is you take k sets, okay? So you're basically forming k sets of characters, and every set size has to be greater than or equals to 2. So let's say we take B and D and C here, and then Y and T here, and then A and F here. Okay, so we're just putting things in these sets, and then I want to use the characters in that set to make a palindrome. And now I want the size of the smallest set to be maximum. So yeah, all that coloring and all that constraints, they were really just very annoying. I think this representation of the problem is much more understandable. So that is the problem. Now how to do it? Well, let's have a look. What is a palindrome, first of all? How do you form a palindrome? So a palindrome is a string which reads the same as from the left as to the right. That means, let's say we had a palindrome like this. That means the first and last character is same. The second and second last are same. And then if it is of length odd, then there is an odd number, an odd character there. So what that means is the number of characters which have odd frequency, right? Because if this character is same as this character, then that means that character's frequency plus equals to 2, right? So that means that here the number of characters with odd frequency is equals to 1. That is for odd length, and is equals to 0 for even length. So for a set of characters to be able to form a palindrome, what we want is the frequency of at maximum only one character to be odd. Now you might be saying that what if one character has odd frequency but length is even? Well, that is not possible because even plus even plus even plus one odd is not even. So this is the condition we need. So now, I mean, we didn't exactly needed it, but this is what we needed to understand, that to form a palindrome, we need, so to form a palindrome of length n, right, n can be even or odd, we want n by 2 pairs of equal characters, and then that one remaining unequal character that can be picked off from anywhere. So that is just irrelevant. So now let's see how we can form these sets, right? So now instead of permutation and all that, we just need to worry about the frequency of the characters that are coming in the set. So let's say I say k is 3, right? Or let's say k is 4. Then that means we have to have 2 pairs of equal characters in every set at least. Sorry, if k is whatever, I forgot that k is some value. So let's just erase all that. So we want to end, right? This is a string, and let's say k was 2, so we have to take out 2 sets, and let's say we are trying that every set has at least, or I'm gonna call that length, at least 4 characters, right? So if every string needs to have at least 4 characters, or just 4 characters, because if I can satisfy for at least 4, I can obviously satisfy for 4, right? Okay, so if I have to do that, then I want 2 pairs of equal characters for every set, right? So let's say A occurred 3 times, B occurred 2 times, and C occurred 2 times. Then what I can do is, first of all, take 2A, right? And let's say D also occurs 1 time. So first of all, I can take 2 A's, and then I can take 2 B. Okay, and then I can take 2 B, and here you can see that using this set of characters I can make a palindrome. And then for the next set I will take C and D, so 2C and 2D, and then again I can form the palindrome. So where are we so far? So we have observed that for a palindrome we just want that the number of characters with frequency which is odd to be less than equals to 1, right? So now and we also have a simple greedy method to actually form these sets, right? And then we will be able to make a palindrome out of them, but we don't have to do that because the problem doesn't ask of that. So since we can form a palindrome using this, that means we can have length 4. So 4 is answer at least. Then we can try 5, right? We can also try 5, and for 5, since 5 is odd, right, we really want to pair up to 4 length, and then we can pick off the remaining ones. So here, as you can see, we have an extra A, we will just put here, we get length 5. Then we have an extra E, we put here. It doesn't matter which we pick, we can pick E here, A here. So what this means is, that for some length, right, we tried for 4, we tried for 5, we are able to figure out if we can form the set with the given constraints, that we need k sets and every set has length greater than equals to L, and the characters in it can form a palindrome. So if we can do this, it is a common pattern. You might already be thinking about it. What it is? It is the same thing. We know that we can check for some length L, if we can form that length, right? So if we can form this length, then that means we can also form length from 1 up to L. So we will just have to check in L plus 1 to infinity, or whatever is the maximum possible. I'm just gonna call it max. And if I cannot do that, then that would mean that I'll have to check inside here only. This is binary search, right? So we can just binary search on L, which is the answer, basically the maximum length of the minimum set size. So let's see how I did it. Where we are. Okay, so this is taking input. Then I form the frequency set because frequency matters. Then minimum length would be obviously 1, right? I can always form sets of length 1. Wait, was there any condition for length greater than 1? No, I made that up. Okay, I'm an idiot. So yeah, but yeah, I still think this set explanation was better rather than thinking in colors. So I first of all calculate the frequency, then I have the minimum length that the sets can have, and the maximum length, which will be n by k, the floor division obviously, because if let's say n was 5 and k was 2, then I can only have a maximum length of 2, because if I were to take 3, then one set will have 3 and the other one will have 2, right? So that is not possible. We are checking for the length of length of the least big set, the smallest set. So yeah, we are checking for mid. First of all, I clone the frequency array, and now I'm just doing this assignment that I explained. So I go through every character. Okay, I go through every character, and this is the required number of pairs that I need. Now obviously if it is odd, it doesn't matter. I still need, for 4 I need 2 pairs, for 5 again I need 2 pairs. So this is the required number of pairs. This will be a value which will keep on incrementing, and once it reaches required, then that means count increases. Okay, and the current character that I'm checking is A. So now while count is less than k and character is less than equals to z, I'll be able to do these things. First of all, I take out what is the required number of pairs I need and what is the maximum number of pairs I can get from this character. So among those I will take the minimum, because if there were 10 characters for A and I only needed 3 pairs, which means I needed 6 characters, so I will only want to subtract 6. So I get that, I add this into sum. Remember, sum represents the number of pairs, and then I remove the characters from that. After that, now if sum have reached required value, then the number of sets that I have formed increases, and again make the sum 0 and continue. And now if the current frequency has become 0, this will basically not do anything or become 1. Now if the frequency is less than equals to 1, then that means it cannot contribute any more pairs. So I'll just increase the character, I will check the next character and continue. And after doing all this, if I have covered greater than equals to k characters, this will actually never go beyond k. Equals condition will also work. In that case, answer is at least mid, and then I will move the search space from mid plus 1 to high, otherwise low to mid minus 1, if I was not able to do it. And then in the end I just print the answer. Okay, I will give us, no, I'm not even gonna give hint for that, maybe I'm wrong. So let's talk about this MinOr Tree. So in this we are given a graph, a connected weighted graph. So we are given a connected weighted graph, 1 2 3 4 5, and everything has a weight. So w1 w2 w3 w4 w5 w6, and just like we have minimum spanning tree, what minimum spanning tree is, we basically choose a subgraph. So that means we choose all the vertex and some of the edges such that the resulting subgraph is a tree. So basically it can become 1 2 3 5 and 4. So this can be one of the subgraphs, right? And the minimum among that would be the minimum spanning tree. And what does minimum mean? Obviously the sum of the weights. But in this case we want to minimize the OR of the weights. So basically if we have w1 w2 w3 and w6, instead of minimizing this summation, we want to minimize the bitwise OR. This is what we want to minimize. So how can we do it? Well, first of all, we are gonna assume that we can find a minimum spanning tree of something. Not even minimum. First of all, we need to have a function which, you know, checks if everything is connected. If everything is connected, then that means we can form a minimum spanning tree, right? That is one requirement we need. So that can be done by simply DFS. Okay. So now let's see how we can minimize this OR. So whenever you have bitwise problems, right, it is always wise to think in the bits, because if we have some number, right, if we can remove this bit, then it is better to remove this bit than, you know, sacrificing this bit for some bit here, because the value of this bit, which is like 1 2 3 sorry 0 1 2 3 4 5 6 7, this, the value of this bit is 2 to the power 7, and value of all these bits combined is 2 to the power 7 minus 1. So what that means is it is always optimal to try to avoid adding this bit, right? If we can avoid this bit, we will avoid this bit, even if we have to sacrifice some bits here, because it is optimal, because this is much better than them. So we will try to avoid bit from the most significant bit side. So that is the left side. So what do I mean by avoiding bits? So basically, if you want to avoid some bit, right? Let's say the 7th bit, then we want to remove all the edges which has in their weights the 7th bit on. So for example, so let's say this is the 7th bit I'm drawing, okay? So these are some of the edges. I will remove all these 3 edges because they have this bit on. And after removing these edges, I will check, can I still form the spanning tree using these remaining edges? If I can, then that means let's just remove that edge. Sorry, let's just remove all the edges with that bit. Hence, I will not get that bit in my bitwise OR, right? Because if I want to avoid getting that bit, I need to avoid even a single number that has that bit. That's how OR works. So where was I? Yeah, so we'll just remove all of them, and if after removing all of them I'm still able to form a minimum spanning tree, I will just keep them removed and move on and try for the next bits. If however I'm not able to do, even then we might have to remove some of them, but that does not matter. For now I will keep all of them, because if I'm using that bit, might as well use every other edge, right? Now of course I will remove it later on depending on the other bits that come and the condition what happens there. But yeah, just for this bit, as far as this bit is concerned, I'm keeping them. And I will keep doing this, and after this I will have removed a lot of edges, and the bitwise OR of all the remaining edges will be my minimum spanning, whatever it is. Yeah, minimum spanning OR tree. So yeah, that is the way to implement. All you need to know is you need to do a DFS in order to check if you can still form a spanning tree, and yeah, nothing else. Now I did it using the MST algorithm. That was a little unnecessary, but doesn't matter. So I take in the input, right? So what an edge is UVW. I've overloaded less than operator for sorting and input operator for input. So I take in the input, and then I go from the most significant bit, and if that bit is on in the edge, I will not take it, otherwise I will take it. And then I'm doing classical MST here. You can do simple DFS to see if after removing all the bits with all the edges with this bit on, can I still form a MST. So here I'm returning -1 if I cannot form by doing some change here. And if that is the case, if I can form, then I'm keeping all the removed edge removed. So I'm just updating edges to be equals to current. Otherwise, I'm not removing them. And after doing all that, I'm just recalculating the MST. Okay, now this was obviously way too unnecessarily slow. There was too much computation, too much unnecessary computation, but this also works. It would be hilarious if it gets hacked. But now here, all you need to do is take all the bits that were actually accepted and OR all of them, and that would be the answer. I'm doing bitwise, I'm doing classical MST, and then I've replaced plus with OR. Really unnecessary. So yeah, this was problem G, and yeah, these were the solutions for A, B, C, D, and G. And with that, bye.